Welcome back. In the last video, we got set up, starting to get ready to model our first custom data set. And I issued you the challenge to try and replicate the tiny VGG architecture from the CNN Explainer website, which we covered in notebook number 3. But now let's see how fast we can do that together, hey? I'm gonna write down here section 7.2. And I know we've already coded this up before, but it's good practice to see what it's like to build PyTorch models from scratch. Create tiny VGG model class. So the model is going to come from here. Previously, we created our model. There would have been one big change from the model that we created in section number 3, which is that our model in section number 3 used black and white images. But now the images that we have are going to be color images. So there's going to be 3 color channels rather than 1. And there might be a little bit of a trick that we have to do to find out the shape later on in the classifier layer. But let's get started. We've got class tinyVGG. We're going to inherit from nn.module. This is going to be the model architecture, copying tinyVGG from CNN Explainer. And remember that it's quite a common practice in machine learning to find a model that works for a problem similar to yours and then copy it and try it on your own problem. So I only want 2 underscores there. We're going to initialize our class. We're going to give it an input shape, which will be an int. We're going to say how many hidden units do we want, which will also be an int. And we're going to have an output shape, which will be an int as well. And it's going to return something none, of type none. Then if we go down here, we can initialize it with super dot underscore init. Beautiful. Now let's create the first conv block. So conv block 1, which recall will be this section of layers here. So conv block 1, let's do an nn.sequential to do so. Now we need conv relu max pool. So let's try this out. And then conv 2d, the in channels is going to be the input shape of our model, the input shape parameter. The out channels is going to be the number of hidden units we have, which is from, I might just put enter down here. Input shape, hidden units. We're just getting those 2 there. Let's set the kernel size to 3, which will be how big the convolving window will be over our image data. There's a stride of 1 and the padding equals 1 as well. So these are the similar parameters to what the CNN Explainer website uses. And we're going to go nn relu, and then we're going to go nn conv 2d. And I want to stress that even if someone else uses like certain values for these, you don't have to copy them exactly. So just keep that in mind. You can try out various values of these. These are all hyperparameters that you can set yourself. Hidden units, out channels equals hidden units as well. Then we're going to go kernel size equals 3, stride equals 1, and we're going to put padding equals 1 as well. Then we're going to have another relu layer, and I believe I've forgotten a comma up here. Another relu layer here, and we're going to finish it off with nn.maxpool 2d, and we're going to put in the kernel size equals 2, and the stride here equals 2. Wonderful. So, by the way, for maxpool 2d, the default stride value is same as the kernel size. So let's have a go here. What can we do now? Well, we could just replicate this block as block 2. So how about we copy this down here? We've already had enough practice writing this sort of code. So we're going to go conv block 2, but we need to change the input shape here. The input shape of this block 2 is going to receive the output shape here. So we need to line those up. This is going to be hidden units. Hidden units. And I believe that's all we need to change there. Beautiful. So let's create the classifier layer. And the classifier layer, recall, is going to be this output layer here. So we need at some point to add a linear layer that's going to have a number of outputs equal to the number of classes that we're working with. And in this case, the number of classes is 10, but in our case, our custom data set, we have 3 classes, pizza, steak, sushi. So let's create a classifier layer, which will be nn sequential. And then we're going to pass in nn.flatten to turn the outputs of our convolutional blocks into a feature vector, sorry. And then we're going to have nn.linear and the in features. Do you remember my trick for calculating the shape for in features? I'm going to put hidden units here for the time being. Out features is going to be output shape. So I've put hidden units here for the time being because we don't quite yet know what the output shape of all of these operations is going to be. Of course, we could calculate them by hand by looking up the formula for input and output shapes of convolutional layers. So the input and output shapes are here, but I prefer to just do it programmatically and let the errors tell me where I'm wrong. So we can do that by doing a forward pass. And speaking of a forward pass, let's create a forward method, because every time we have to subclass nn.module, we have to override the forward method. We've done this a few times, but as you can see, I'm picking up the pace a little bit because you've got this. So let's pass in the conv block 1. We're going to go x, then we're going to print out x.shape, and then we're going to reassign x to be self.conv block 2, so we're passing it through our second block of convolutional layers. Print x.shape to check the shape here. Now this is where our model will probably error, is because the input shape here isn't going to line up in features hidden units because we've passed all of the output of what's going through conv block 1, conv block 2 to a flatten layer, because we want a feature vector to go into our nn.linear layer, our output layer, which has an out features size of output shape. And then we're going to return x. So I'm going to print x.shape here. And I just want to let you in on one little secret as well. We haven't covered this before, but we could rewrite this entire forward method, this entire stack of code, by going return self.classifier and then going from the outside in. So we could pass in conv block 2 here, conv block 2, and then self conv block 1, and then x on the inside. So that is essentially the exact same thing as what we've done here, except this is going to benefits from operator fusion. Now, this topic is beyond the scope of this course. Essentially, all you need to know is that operator fusion behind the scenes speeds up how your GPU performs computations. So all of these are going to happen in one step. Rather than here, we are reassigning x every time we make a computation through these layers. So we're spending time going from computation back to memory, computation back to memory, whereas this kind of just chunks it all together in one hit. If you'd like to read more about this, I'd encourage you to look up the blog post, how to make your GPUs go burr from first principles. And burr means fast. That's why I love this post, right? Because it's half satire, half legitimately like GPU computer science. So if you go in here, yeah, here's what we want to avoid. We want to avoid all of this transportation between memory and compute. And then if we look in here, we might have operator fusion. There we go. This is operator fusion, the most important optimization in deep learning compilers. So I will link this, Making Deep Learning Go Burr from First Principles by Horace Hare, a great blog post that I really like, right here. So if you'd like to read more on that, it's also going to be in the extracurricular section of the course, so don't worry, it'll be there. Now, we've got a model. Oh, where did we forget a comma? Right here, of course we did. And we forgot another comma up here. Did you notice these? Beautiful. Okay, so now we can create our model by going torch or an instance of the tiny VGG to see if our model holds up. Let's create model 0 equals tiny VGG. And I'm going to pass in the input shape. What is the input shape? It's going to be the number of color channels of our image. So number of color channels in our image data, which is 3 because we have color images. And then we're going to put in hidden units equals 10, which will be the same number of hidden units as the tiny VGG architecture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, we could put in 10, we could put in 100, we could put in 64, which is a good multiple of 8. So let's just leave it at 10 for now. And then the output shape is going to be what? It's going to be the length of our class names, because we want one hidden unit or one output unit per class. And then we're going to send it to the target device, which is of course CUDA. And then we can check out our model 0 here. Beautiful. So that took a few seconds, as you saw there, to move to the GPU memory. So that's just something to keep in mind for when you build large neural networks and you want to speed up their computation, is to use operator fusion where you can, because as you saw, it took a few seconds for our model to just move from the CPU, which is the default, to the GPU. So we've got our architecture here, but of course we know that this potentially is wrong. And how would we find that out? Well, we could find the right hidden unit shape, or we could find that it's wrong by passing some dummy data through our model. So that's one of my favorite ways to troubleshoot a model. Let's, in the next video, pass some dummy data through our model and see if we've implemented the forward pass correctly, and also check the input and output shapes of each of our layers. I'll see you there.